So today the plan is to go over chapter 15, which discusses body composition and nutrition for sport. And then we will go over the exam number 2 review to make sure that everybody has an opportunity to do well this coming Monday. Again, the exam will be available to you for this coming week, but we will not be meeting on Monday in case people need that time block to do the exam. It'll be the same as last time, 50 questions, 10 from each chapter in the order presented. So we can get to any other questions later on today if you have them. But I would like to begin chapter 15, which talks about body composition and nutrition for sport. And one of the things that we want to clarify is that it is nutrition for sport. This implies that it's not nutrition for everybody who's normal, or it's not nutrition for people who aren't participating in sport. It could be the case that the suggested body composition and nutrition for somebody who is doing sports might be different than the body composition and nutrition suggestions for somebody who is not doing sport. For instance, even though my guys are young, the amount of activity that they're doing in the gym, they're usually about, and now maybe I'll just say for my older guys are pumping about, I would say 4,000 calories a day, especially my older athlete, Yusuf. He works so hard, and then he'll go home and he'll work at home, and then he's got school that he's got to deal with, and he's telling me that he plays spike ball with his friends at school, and he's just spending so many calories. But the normal individual who's not performing, sport activities is more likely about 2,000 calories. All right, so these suggestions for sport performance are going to be very different than the suggestions for somebody who is just, performing activities of daily living. Remember, 50% of the country does not do daily physical activity. And for those individuals, excess calories are going to be stored as adipose fat. So for the most part, so what we want to do is we want to discuss in this chapter nutrition for sport performance, particularly. Everybody's seen sumo wrestlers. Sumo wrestlers are gigantic, and most of them would be technically obese, but some of that weight is there to help improve sport performance. Same thing with NFL players, right? Momentum, which has to do with Newton's first law of motion, momentum is equal to mass times velocity. And momentum, the definition of momentum is resistance to stopping. So if a football player is an offensive lineman and he's pushing the defensive lineman, that offensive lineman wants to keep moving forward, and it wants to push the defensive lineman away from the quarterback. And that offensive lineman does not want to stop, wants to have a lot of momentum. So not only does the offensive lineman have to move very quickly off the ground, the 6-inch punch has to be very quick. There also has to be a good amount of mass behind it. So for a football player to have a good amount of mass, or for a sumo wrestler to be massive, means that they're going to be more difficult to stop once they start moving. And that's going to be an advantage for that particular athlete. So some athletes, you're going to want to have a large body mass, but force is equal to mass times acceleration. All right, so the forces on the body are proportional to the masses, or the mass of the body, because gravity, which is accelerating that body to the ground, is going to make it so that there's a force due to that mass. So the more massive you are, the more force is going to be put on your bones, or the more force that you need to move this mass. And if that's the case, then for athletes like gymnasts or pole vaulters or runners or dancers or rowers or people that need to move their mass through space to do their particular sport may be at a particular disadvantage if there's too much mass. So the goals of the sport and the sport that you're involved in and the particular position in the sport, and there's so many different variables that would dictate what the appropriate body composition and nutrition for sport performance is. So we'll get into that a little bit more throughout this chapter. The chapter is organized like this. The beginning of the chapter talks about various tests or assessments for body composition. We're going to specifically talk or use bioelectrical impedance in our course because I think it's just much easier to present it to you as part of the lab. But you may have heard of hydrostatic weighing or air displacement plethysmography, or the use of X-ray or electrical signals through the body to assess the amount of fat mass versus the amount of fat-free mass. All right, so that's what body composition is assessing. The percentage of the body that is fat compared to the percentage of the body that is not fat. Now, the things in the body that are fat-free mass are muscle and bone and blood and cartilage and the tissue of your organs. So there's a pretty good amount of the body that is not included in this fat-free mass. Bone is usually about 17% of the fat-free mass weight, and typically values of your percent body fat or your fat mass is going to be somewhere between 5, which is very low, to, say, for instance, above 30, which is going to be obese. So you're going to have values of your percent body fat or your fat mass or your percent body composition of between 5 and 30%. And you might even have higher than 30%, but that's going to be of cases where people are relatively obese. All right, so these body composition standards, what percentage an individual should be in regards to their fat mass, all right, might be different in each sport. It might be different because of you're maybe trying to cut weight. Maybe you're a wrestler or a boxer. In that case, the standards might change from performance to performance or week to week, and it may be that your optimal weight is easier for you to attain because you are a high or a low responder. The second part of the chapter is dealing with nutrients, different types of nutrients. So we'll talk about the nutrients that we'll discuss are carbohydrate, protein, and fat. Carbohydrate, protein, and we'll make fat first. Carbohydrate, fat, and protein. And when we're talking about our diet protein, we're talking about percentages somewhere along these lines. 50% of your diet should be about carbohydrate, and 30% of your diet should be about fat, and 20% of your diet should be from protein. Now, if you're going to do a little bit of activity, and you remember that carbohydrate is like the gasoline for those individuals that are going to do higher end physical activity, you might want to increase this percentage of carbohydrate in the diet to about 55%, maybe even more, 55 to 70%. And that means that you would reduce percentages of your fat and protein. So we're going to talk about carbohydrate, fat, and protein and what it means to get 30% of your diet with fat. But remember, you don't store excess protein. And fat stores are used for thermodynamics, but also for fuel. So predominantly you want your diet to be made up of carbohydrate and fat. And rather than utilizing protein for fuel, you want to use protein for tissue remodeling and repair. The last part of the chapter talks about water and electrolyte balance, but we don't talk too much about it. I will talk a little bit about the difference between water and Gatorade, or when you would use water and when you would use Gatorade. Remember, there's a couple of different reasons to hydrate. All right. Number one is because water tastes good, or because whatever you're drinking tastes good. But another reason is to hydrate. So if you're working out in a very dry environment where you're sweating a lot, you may need to hydrate. And if that's the case, you would want to have a solution that is closer to water. But if you're hydrated and you're worried about losing muscle glycogen, then you might want to have Gatorade. So my athletes are working out in a 70-degree environment every day. They're indoors, so there's no change in temperature really. It's not hot, it's not cold, it's not too humid. They're never really doing high-end endurance training, so they're never sweating a huge amount unless we're doing hypertrophy training and circuits with our weights and dumbbells and stuff and our kettlebells. So for the most part, the gymnasts aren't losing a huge amount of water. So I want them to make sure that they have enough muscle glycogen. So for my athletes, I would suggest Gatorade. Every 20 minutes, a little sip of Gatorade. Whereas for an individual who is exercising in Arizona, a very dry environment where they're losing lots of water from sweat and evaporation, maybe you might want to consider water replacement there. So depending upon what you're doing, you would choose a different fluid to maintain fluid balance in the body. And then there's a suggestion about the diet for athletes, and we'll talk a little bit more about that and break down these carbohydrates, fats, and proteins so you understand what people need and when they need it in terms of those nutrients. So that's pretty much what the chapter is going to cover. And the chapter starts with understanding body composition. So remember, this is important primarily because of this equation, the resting metabolic rate equation. Resting metabolic rate. And I think that this is one of the most important equations in all of, I guess, exercise physiology or whatever we're working on, weight management, understanding this energy in, energy out relationship that is confounded by, what we talked about the other day with sugar and all of these other variables. But this equation here, to me, is the new weight management equation. It's the way to understand the whole impact of energy in and energy out, and how to manage this energy out aspect. And it has to do with your fat-free mass. So I am 74 kilograms. And just so you know that I'm 163 pounds, and the way to go from pounds to kilograms is to divide by 2.5. So I'm 74 kilograms, and this is the value here that I'm going to use to plug into this resting metabolic rate equation right here. All right, and that's going to tell me what I'm spending in terms of energy at rest. So eventually we're going to have to figure out what this fat-free mass value is. fat-free mass is everything that is not free of fat, which is pretty much my fat mass, all right, or my body weight minus my fat mass. So how do I assess fat mass? Well, there's a bunch of different ways to do it, and they're all based on these models. Now, the definition of a model, or what a model is a way of describing something, but a model is always more simple than what it's describing. That's why it's a model. You can't have all of the variables in a model, otherwise the model would be actual reality. So a model is a way of simplifying things so that we can understand it. All right, so I'm going to show you a couple of different models of the composition of the human body. All right, there's a chemical model. So you could think of the body as a biochemical, I guess, machine where you have all these enzymes and nutrients working together to provide fuel and hydration, and the enzymes and minerals needed to catalyze chemical reactions and sodium potassium ion channels and calcium and magnesium coming out of the sarcoplasmic reticulum and eventually leading to heartbeats and muscle contractions. We could also think of the body as broken down into an anatomical model where I have things that are my fat mass and everything else that is not my fat mass. And another way of thinking of it is, as opposed to breaking things down to their fat-free mass constituents, is to take all of these things and to lump them together into what's called fat-free mass. And so this adipose tissue and around the organs fat is all going to be called the fat mass. And for an individual who is a highly developed athlete, they're going to have a fat mass between, say, 5 and 18% or so. Therefore, their fat-free mass is going to be anywhere from 95 to, I don't know, what, 82% or something like that. Now, who's to say that everybody's fat mass is exactly the same as everybody else's? Or who's to say that the density of everybody's fat-free mass is going to be the same? So to make that assumption, you know, that assumption might not hold true for everybody, but this is just a way of modeling or describing the human body. And it is this model here, this two-component body model, that is the basis of all of these body composition assessments. We're assuming that the body is made of stuff that's fat and stuff that's not fat. Of the stuff that's not fat, about 17% is bone. All right. And the rest of the fat-free mass that's not bone is going to be obviously muscle, organs, blood, cartilage, ligament, tendon. All right, so how do we go about figuring out how much or what percentage of the body is fat versus fat-free mass? Well, we have various different ways of doing that. We have field assessments. Let's get rid of this. We have a number of different ways to do this, all right? We have field assessments and laboratory assessments. One interesting variable that we could use to give us some information is the body mass index. The body mass index is the body's weight in kilograms divided by the height squared, weight in kgs divided by the height squared. Now, and it's the height in meters, by the height in meters squared. So one of the things that you're going to have to be able to do is to be able to convert units from pounds to kilograms, if you're not good at doing this, then maybe what you do is you start your very first value with kilograms, and then can do all of your assessments and all of everything else. But that resting metabolic rate equation, everything is in kilograms. So in order to go from pounds to kilograms, you divide pounds by 2.2. Pounds divided by 2.2 gives you kilograms. So if I am 163 pounds, and we'll use these variables, or these, values for the rest of the day, divided by 2.2, that is 74. So we'll use this number 74 to represent me for the rest of the day. 74 kilograms, that's what I weigh. All right, and if you're going to go from height to meters, from inches to meters or whatever, or feet to meters, then we want to know that 1 inch, let's go clear these things here. Whoopsies, erase. You also want to be aware that, I guess, the easiest or the most important thing is 1 inch is equal to 2.54 centimeters. And then we can do our conversions and all of that stuff, but these will be relatively important conversions for you. So 1 inch equals 2.54 centimeters, and then multiply that by 12 to tell how many centimeters are in a foot, and then how many blah, blah, blah. We'll be able to figure all that stuff. So these are your conversions, all right? So body mass index equals weight divided by height squared. And body mass index is used, is used to give an assessment of whether or not somebody is overweight or underweight. Now, it's very difficult to tell whether or not an individual is obese, or whether or not an individual's body composition is high, or whether or not they're unhealthy, because this weight right here that is part of this body mass index calculation, the weight doesn't tell me whether or not these kilograms are 50% body, 50% fat-free mass or 20% fat-free mass. So if you're looking at an article that only uses body mass index as its grouping or as its way of binning individuals into obesity or not obese or into weight classifications, be careful, because it's not a real assessment of body composition at all, because it can't tell, or it doesn't tell, whether or not these kilograms are fat-free mass or fat mass, or the percentage of them. So we want to use other resources that are above and beyond just height and weight to tell whether or not people have the correct percentage of fat-free mass and fat mass. When you look at the research, especially in endurance type activities, increased body fat results in decreased performance, particularly because increased body fat equals increased mass, and increased mass equals increased force, and also requires, so increased force on the body means more impact, more jostling, more breakdown of tissues, more eccentric micro damage with eccentric muscle contractions. So it requires more force to move it, and there are more forces going through the system, so it's going to break down the system faster. So the ways that we do it are through lab measures and field measures. Lab measures are those measurements that need to be done in a lab setting, predominantly because the equipment is very complicated. So like the hydrostatic weighing, I'm sure people have heard about hydrostatic weighing, and we'll talk about it in the next slides. But in order to do hydrostatic weighing, you need a huge tank of water, and that person is going to have to be submerged into a tank of water. They're going to have to blow all of their air out. In any event, you're going to need a lab room within your college or whatever that you can fill or place this hydrostatic weighing chamber. And at Assumption, we don't have that lab space. Well, that's the reason why we don't teach you densiometry. And densiometry is the metric or the measurement of body composition using density, the body's density. All right. And as we talk about it, we'll learn a little bit more about how this happens, but we don't do it in our lab because we just don't have enough space. I just started a fish tank about a year ago, and it's taken me a good amount of time to figure out actually how to make it so that the water doesn't get algae and that I can maintain the water. So there are complications associated with, even if you have the lab space, how do you keep the hydrostatic weighing chamber clean? How do you change the water? What happens if there's a leak in the hydrostatic weighing chamber? Obviously, water damage could destroy an entire building. So there are drawbacks to hydrostatic weighing. Also, I don't know how to do hydrostatic weighing. I've never done it before as a technician. If that's the case, I'm going to have to be trained. So there's space, there's money, there's maintenance, there's training, and all of a sudden there are costs and difficulties with presenting laboratory methods of doing body composition. So what we're going to do is present field methods, methods that you could do without a lab, methods that you could do in the metaphorical field. So if I went to a grassy field and I had my skin calipers, I would be able to give you your body composition. I don't need a lab. I could do it out of the back of my car, whatever. I could do it in a field. So there are laboratory methods of assessing body composition, which need complicated equipment. And then there are field methods, or much faster, easier ways of measuring body composition that we're going to present. Usually in lab, you'll be taught the skin fold method. But I believe in teaching you this bioelectrical impedance method because it's much easier, much faster. These skin fold calipers that you use are expensive, much more expensive than the bioelectrical impedance scale that you can get at Walmart for 20 bucks. And this method here of using the skin folds requires me to pinch the fat in somebody's belly, upper back, thigh, and for the most part, people don't really want to do that. And the equipment that we have in our lab to even do this field measurement of skin fold thickness is antiquated. We have these plastic little calipers that aren't going to be very accurate and effective anyway. So I don't see why we should do that. I think bioelectrical impedance is a field method that is far less invasive, or not invasive, but far less impactful to the participant. And it's much easier. But there are drawbacks and there are sources of error for each one of these particular assessments. And we'll talk about them. Not only do you want to know how the assessment is done correctly and what are the benefits of doing hydrostatic weighing, but you also want to know why we don't use them. What are the drawbacks for hydrostatic weighing? And ultimately, if you have your own business or if you have your own athletes and you need to assess their body composition, which one of these would you choose? You have them all at your disposal. Each of them are going to be useful for their own right. But why would I choose bioelectrical impedance versus skin fold or air displacement plethysmography to measure body composition? And that's a choice that you as a clinician are going to have to make. And it could be because of money, training, space, whatever it is. But there are multiple ways to skin the cat. Good thing it's not only hydrostatic weighing, because if somebody is hydrophobic or afraid of water, I can use some other resource. All right, good thing for these scales that I can buy at Target, because if I didn't have easy ways of doing bioelectrical impedance, how would I teach you how to do body composition in a lab that doesn't really have too many lab materials? So I have more than one option, which means that in your lab, if you were to open up a practice that manages weight for individuals, in your lab, you're going to have more than one way to measure this. And you could also use things like waist to hip ratio, right? These are also other ways of assessing weight. All right, but doing the waist to hip ratio, I don't think is necessarily, again, an assessment of body composition, because it doesn't break down the percentage of this weight that's fat mass or fat-free mass. So body mass index and other anthropometric measurements may give you an assessment of overweight versus underweight, but it won't be a body composition method. So just be aware of that. So if you see an article that only uses body mass index, or that only uses waist to hip ratio to bin people into obese versus not obese, then you want to be careful with only using body mass index as your indicator. All right, so you want to do a concurrent validity study. Usually you'll see that a study will have one of these methods of body composition assessment, and they'll also use body mass index to use as a validation measurement for your body composition measurement. All right, so oftentimes they'll use both, but they'll very seldomly use body mass index by itself. Okay, so the next slide goes into each one of these assessments. One way to assess body composition is to measure the body's density. So the density of water is 1. And things that are more dense than water tend to sink. And things that are less dense than water are going to float. So your fat mass has a density less than water, and that's going to be 0.9. And your fat-free mass is going to have a density that's higher than 1, and your fat-free mass is going to sink. So what they're going to do is they're going to take your weight inside and outside of water, your water weight or your weight outside of water, and they're going to subtract that to your weight in water. And when you're in water, they're going to take this little like chair, and the chair is, it's going to be attached to this meter. All right, it's a meter, and then there's this like a string, and then there's a chair, and the chair is attached to the like this string. So you're going to sit in the chair, and then you're going to be dunked underwater, and then they're going to measure you outside of water, and then when they dunk you in the water, they're going to measure you again, and the weight outside of water is going to be compared with the weight inside of water. And because some of your body, the fat mass is going to float, the weight outside of water is going to be much higher than the weight inside of water. And the comparison of the two is going to give you a sense of your body's density, how dense your body is. Bodies that are more dense are going to have less of a difference between the weight outside and inside of water because there's more fat-free mass and less that's floating. But a body that has a higher fat mass is going to have a greater difference in the weight outside and inside of water. And that's pretty much how hydrostatic weighing works. This is the most commonly used method of body composition because it's the most accurate. But there are some limitations. Number one, I don't have one of these chambers. We don't have one in Assumption, so we just can't do it. But there are other issues associated with the hydrostatic weighing. For instance, the way that you do it is you have to have somebody come in. First of all, they're not clothed. They have to have very little clothing on because sometimes air can get trapped in the clothing. Sometimes air can get trapped in the hair here, and air floats. So if there's air in my clothing, if there's air in my gastrointestinal tract, then that can compound or confound these results. So the individual has to have a particular diet on the day that they're going to come to do this that is very low in gassy producing foods like legumes and soda. They're going to get into this little chamber and they're going to be sitting down on some type of device, and they're going to have to breathe out all of the air in their lungs because the air in your lungs is going to make you float. They have to breathe out all of the air in the lungs. They're going to duck their head way under this water, and they're going to stay as still as possible, still as they can, so their body weight can be measured. But who's to say that they're going to be able to blow all of the air out of their lungs? You have the residual volume of your lungs. If I can't blow all of that air out, well, then I'm not going to be able to get an accurate measurement because my body's going to be floating too much because of the air. One of the things with COVID, they said, hold your breath for 10 seconds. If it's difficult for you to do it, it could be one of the symptoms of COVID. Or what happens if people are hydrophobic and don't want to go underwater? Or when they go underwater and they blow all of their air out of their lungs, it could be the case that they get a little bit nervous and don't want to stay underwater long enough for the technician to be able to make the calculations. Or like we said, it could be the case that individuals ate foods that day that make it so that they have too much air in their gastrointestinal tract. That's going to confound the results. And then once we're done doing this particular assessment, we have to convert. You're going to have to convert the value that you get, which is going to be given in body density. When you do hydrostatic weighing, actually, when you do your skin calipers as well, it will give you a value of body density, not body fat. When you use the hydrostatic weighing method, you're going to get a value that represents the density of your body, and you're still going to have to convert that to % body fat. And like any model or like any conversion, it's going to result in some type of error. Remember, this is only an estimate. In order to actually measure your body fat accurately and not estimate it, what you'd have to do is take the body's tissues out of the body. You'd have to separate the tissues. You'd have to probably put the person in a big blender, all right, blend the tissues down, and then you'd have to put somebody or that person into a big centrifuge. And what would happen is the centrifuge would separate the fat, protein, carbohydrate, water, and minerals in that body. And then you'd be able to tell exactly what the % body fat is, but we can't do that. So the only way that we can do it is by assessing or by using some type of conversion or indirect method. None of what we're doing here in terms of the assessment of body composition is direct. A direct method would be if we spun the person down in a centrifuge and we're actually able to see the actual percentage of body fat. But we can't do that because the person would be dead. So we can only do indirect measurements. Indirect means that there is going to be some type of process. Once we get the data, there's going to be a process that we need to convert that data before we understand body composition. So we'll get a value of body composition, but only after some conversion is done. And with this step of conversion, this indirect method, there's always going to be some type of estimation error. So right now, we're only estimating body composition using densiometry or skin calipers or whatever. All right, so that's a limitation. We're not exactly measuring percent fat. We're estimating it. All right, and it's also assuming that when you look at this component here, this fat mass versus fat-free mass, we're assuming that using this indirect method or these measurement methods, that everybody's fat mass is the same density and everybody's fat-free mass is the same density. But that's not necessarily going to be 100% the case. So there are limitations in the assessment of body composition using densiometry based on the equipment and based on the conversion of the data that you get from using the equipment to the actual value that you're looking for. So we're never going to be perfect. There's always going to be some semblance of error in our measurements. So how much error is too much error? Well, the way I look at it is if we're already going to have error and there's no way around the fact that I'm going to have some error in my measurement, why don't I just use in our lab the easiest measurement? Because no matter what I use anyway, there's going to be error to it. So let's mitigate the error. Let's use the one that is fastest to do, that is easiest to do in terms of psychology. When you tell a person that you're going to use calipers to pinch their skin and tell them how much fat they have, nobody's going to really want to do that, right? But if I just say step on the scale, and it'll tell me your body weight, and it'll give me a couple of other variables. One of them is body composition. Boy, is that psychologically less impactful. Much better for me. So that's why I introduce our bioelectrical impedance. But in the vein of trying to learn more, we may as well go through the other potential field and lab assessments of measuring body composition. So another lab measurement that we could use is dual X-ray absorptometry. And as the method implies, we're going to be using X-rays. Now, X-rays are not just some thing, I guess, or this assessment that we can use randomly. In order to use dual X-ray absorptometry, they made I guess, a change into the protocol over the last couple of years, maybe the last 10 years, that in order to do this, you need to actually have a certification to utilize X-ray technology. It used to be the case that you didn't, and UMass Boston bought one of these dual X-ray absorptometry machines, certified. I have no idea if that's how you spell it. Certified. ED. That's it. Certified. Erase. Certified. There's an R there. There's an R there. Certified. That's it. So you need to be certified to use X-ray and this particular assessment. I don't have an X-ray technician certification. We don't have a DEXA machine in the lab, but the way that it works is X-rays are going to bounce off of things that are more dense. And when you look at a skeleton, you can tell the things that are more dense because they show up white on a in an X-ray. So if I went like this, you'd be able to see that the skull here is the most dense part of this body. And you can see that there are other parts of the body that are less dense, like this muscle mass here, which is my vastus medialis and my vastus lateralis and my gastrosoleus. But you can see the more dense aspects of the more dense tissues are estimated or are shown to be much more stark white. So you can analyze this particular picture and figure out which of these or which percentage of the body is bone and which percentage of the body is these other tissues. And you can get an assessment of your body composition. All right. All right. So pretty much what it's doing is it's quantifying, which is making a number out of, as opposed to describing the composition of your body, which is your muscle mass and fat and bone. And it'll just print out this this analysis, and it will give you your body composition. It's very precise and it's reliable. The word reliable means that you can repeat the value over and over and over. So if I get onto a dual X-ray absorptometry machine and I take my measurement, I'm going to get a body composition, and I'm going to rest for an hour or whatever, and I take the another assessment using the same machine, I'm going to get very, very similar results. So it's quite precise, it's valid, and it's reliable, it's repeatable. But in order to use it, you need to get certification, you need to hire a technician, the technician needs to get certified, which means that person is going to have to pay another person to learn how to do it. You need to have a lab room to be able to house this, and the dual X-ray absorptometry machine they have at UMass Boston, they don't even use anymore. So it's a very accurate and reliable way of assessing body composition, but it's not realistic. But it's one way to do it. All right, now, if I say, for instance, have a bucket of water, all right, here's a bucket. The bucket is filled with water, all right? If I take my hand and I dunk it in the bucket, all right, then what's going to happen is eventually, if I have my hand and I dunk it in the bucket, the volume that is my hand, the volume that of mass that my hand has, okay, when I take my hand and I put my hand in the bucket, the volume of water that is equal to the volume of my hand will spill over the sides of the water, out of the bucket, especially if the bucket is filled to the brim. When I stick my hand in the bucket, I'm going to displace some of the water that's in the bucket. And the amount of water that flows out of the bucket is going to be the same volume as the volume of my hand that goes in the bucket. So some of the water is displaced. And then the volume of water that is displaced, density, is equal to mass times volume, I'm pretty sure. One second. What is the equation for density? Might be mass divided by volume. I found this on the web. Yeah, mass divided by volume. So, my bad. My bad. I'm not always correct. Density is mass divided by volume. So if volume goes up, but mass does not, then the density goes down. So you could have a boat which has a very, very big mass, but that boat takes up a large volume because of the hull. It's going to be less dense than water, and it's going to be able to float. So you can use the volume of water that is displaced and the mass of the body in or outside of water to figure out the density. And then I can convert that density to body composition. Now, similarly, if this was filled with air or it was filled with beanbag, foam, if I stuck my hand in this bucket filled with beanbag foam, again, the little beanbag stuff would fall out of this particular bucket, and the volume of beanbag styrofoam that fell out would also be an indicator of the volume of this hand, and I could do the same thing. So hydrostatic weighing is sort of a water displacement, but air plethysmography or air displacement plethysmography is using this same kind of understanding or philosophy or I guess understanding of the technique. But what's going to happen is this person is going to go into this chamber, and the chamber has this kind of like door to it. So they open up the door, right? They open up the door, and inside the chamber is a specific volume of air. And when I get into the chamber, what happens is there's another chamber here. I don't know if I can draw this effectively. I'm just riffing right here. But in the back, there's like a tube here, and then there's another chamber here. And this tube, all right, there's a little bit of a grommet or like a gasket. And when they open this door and the person sits, all right, in this air displacement plethysmography chamber, right, they're sitting in this chamber. When they get into the chamber, there's an amount of air that leaves the chamber, goes through this grommet, and fills up this chamber. And the volume of air that is in this chamber has got to be the same volume of air as this person, because when this person goes into the chamber, they push air out of the chamber through this gasket into this other chamber that is attached to like a computer. And they use the volume of this air here as their assessment of volume, and then the mass, and then they can figure out density. And then, so this is a density measuring technique that uses the displacement of movement of air outside of this pod as its measurement of its volume and then therefore body composition. Now, this bod pod situation, this air displacement plethysmography, is way easier than hydrostatic weighing because they don't need to be in an environment that they don't have to go underneath water. All right? They don't really have to do too much at all. It's really easy for the subject. What they do is they just sit in this chamber. So it's far less invasive than this technique here. Than this technique here. Much easier, but it still requires them to have this, let's see, a bod pod. Let's show you what it would look like. I don't think there's a picture of it on these slides here. So there's no picture of the bod pod, all right? But it still requires a lab space. It still requires expensive piece of equipment. And because of that, we don't really use the air displacement plethysmography. It's difficult for the operator to use. So again, there's training costs to it. There's lab cost. There's the cost for this bod pod mechanism, expensive. So I can't teach you how to do that either, but It is based on density and volume and the displacement of some type of fluid or air to assess volume. All right. The next assessment that we could potentially do is the skin fold assessment. So the skin fold assessment, I'm sure you guys have seen these calipers before. There's a number of different areas on the body that you would use for males. Let's go for the males. When you're doing your body composition for males, there's 3 sites. The first site for males and females is the thigh. And then for the males, you're going to use slightly different sites. You're going to use the thigh and the belly. Belly, and you're going to use the chest. And for the females, you're going to use the thigh. You're going to use the, not the belly for the ladies, you're going to use the suprailiac crest. I'm just going to go, oh, I may as well write it. The supra, above. The supra is above something. And the iliac is the ilium, the iliac crest, the suprailiac crest. That's the bone that you feel on the side of your waist. It's if you like put your hands to your, hold on one second, suprailiac crest. And then the last one that you would use is your triceps. So the suprailiac crest, 3, and the triceps. And what I'll do is, after we're done with all this stuff, maybe I'll go and open up the body composition assessment within lab to show you how to do this. All right. Now, these calipers are expensive, and they need to be calibrated every year. We don't even have any of these in Assumption. We have these little pieces of plastic that we try to use, but they're not going to be very accurate. So in order to do your body composition using skin calipers, we do need tools. These are about $700, so I don't think that, I mean, I can't afford these. If I'm going to have my own, like, travel around, I guess, like, what is it, like my Uber Fits or whatever, Uber, I drive around and help people out. I don't have enough money to afford one of these skin calipers. And the other problem with this skin caliper assessment is that you have to use them to pinch someone, right? And not everybody likes to be pinched. Not everybody likes to have their skin exposed. And for individuals who are doing body composition who are who are not overweight and obese, this might not be such a big issue, but for 60 to 68% of the country who is overweight and obese, most of the time they're not going to want you to be pinching them. So the other thing is in order for your fingers here to feel what is fat, what is muscle, what is skin, it actually is very difficult to do this assessment and do it correctly. It's taken me years to figure out how to use my fingers here to manipulate the skin the right way so that I get the right value. So although this is somewhat less invasive, it's actually pretty difficult. You have to know anatomy. You have to know technique. You have to know bedside manner, right? Because I don't want to just go up to somebody and say, hey, I'm going to use these pinchers to squeeze the fat on your arm. That's not going to go so well. So you need to know anatomy, but you also need to know technique. You also need to be able to convince people that you're going to be able to do this assessment and it's not going to be embarrassing to them, right? So you have to have like a way of working with people. Now, to get 200 people to come into your lab in a row, or let's say I had to do a body composition assessment. I used to do this for my classes where I would have 45 kids, I'd have an hour, and I'd have to give everybody their body composition. So I used to bring the caliper in, they would come in, they would do the caliper, I'd rip it through, I'd give them their number, I'd tell them to add it, and then they'd go to their body composition, add the numbers together, go to their tables and figure it out. Or what I could do is just bring my bioelectrical impedance scale in. So I will go over this, this skin caliper assessment with you so you understand a little bit more about it, but it's actually not as easy and quick as you would think. All right, so again, I don't use the skin caliper method. Now, what's going to happen is you're going to get these measurements. You're going to get measurements in, say, millimeters. I'm going to get a thigh measurement. Let's say it's 11. Then I'm going to get a belly measurement. Let's say it's 13 millimeters. And a chest measurement, it's going to be 15. I'm going to take these values, 11, 13, 15. That comes out to 39. And I'm going to take this number, 39, and I'm going to plug it into gold standards. I'm going to plug it into equations. I'm going to plug it into graphs that already exist. And when I plug it into the graph that already exists, it's going to tell me my body composition. That's kind of cool, right? There's not too much breathing out that I have to do. There's not too many, I can eat regular food. I just can't do this after I've exercised. I can't do this if my client has lotion on. I can't do this if they have sweatshirt on. Sometimes they'll come in and I'll say, all right, can you take the sweatshirt off? And they say, no, I don't have a shirt underneath. Okay, that's not helpful, right? So there are still setup and pre-test or pre-assessment things that you need to have your subject do, but obviously the equipment that you need, I could carry it around with me. I could do this in a field. All right, it's not very difficult to do, although it does take practice. It's very quick to do. I could get this whole assessment done in 2 minutes. So there are benefits to it, but there are also drawbacks. The major drawback that we have is in our lab, we don't have accurate body composition calipers. So I can't use that. All right, so the next assessment that we could potentially utilize is here. It's bioelectrical impedance. So bio is biological things and electricity. And remember, your body is predominantly water mass, and water conducts electricity, which is a good thing. All right. Water is 70% of what your muscle is. So your muscle is 70% water. The reason why that's important, whereas only 30% of your fat mass is water. All right. 30% fat. Fat is 30% water, I should say. Muscle is 70% water. That helps muscle conduct or transmit the action potential. There should be a C there. Muscle. That helps muscle propagate the action potential. So an individual has more muscle mass is going to have a better ability to allow for this electricity to travel through the body. And what will happen is if there's more fat, fat impedes the electrical signal. So an individual who has more fat is going to have more impedance. What does that mean? Well, what they're going to do is the way that bioelectrical impedance works is you have a person is going to be standing or laying down or whatever, and they're going to have a current, electrical current is going to go in one limb. It could go in their hand, whatever. It's going to go through their body, all the way through the body, and then that current is going to come out of the body in another electrode. And the electrical signal is going to have a particular strength going in. All right, I think it's ohms, and it's going to have a particular strength going out. And what they're going to do is they're going to compare the ohms or the strength of the signal from when it goes in to the strength of the signal when it goes out. Because muscle is predominantly water and fat impedes the electrical signal, an individual who has more muscle and less fat is going to have less difference here in the intensity of the signal from when it goes in compared to when the electrical signal comes out. All right, now that's the reason that we use this bioelectrical impedance is, first of all, the individual doesn't need to be underwater. They're just laying down. They don't have to be shirtless, or there is not really any clothing requirements here. There is a requirement that they're normally hydrated. So if this person in the morning was to drink a gallon, 2 gallons of water before this procedure, and water is the thing that is helping to, I guess, is something that could conduct or impede the signal. If an individual is hyperhydrated during this assessment, it could change the results. So I have this box here is sending an electrical signal. This is my ground, sending the electrical signal into the leg. And that electrical signal is traveling up the body through all of this potential fat-free mass or fat mass all the way up here. It travels out of the arm, and then it comes back out into this computer that's going to assess the body composition, or that's going to measure the impedance or the slowing down or the reduction in that electrical signal. And that's going to be the method by which they use to assess body comp. Now you can see that this electrode is only on the right side of the body, and the electrical signal is going to come up the right side of the body and go out the right side of the body. Or I could take this electrode here and I could put it on the foot. And then what would happen is the electrical signal would most likely come up and it would come back down. So depending upon how many electrodes and where you place the electrodes, it could be more of like a right side body electrical impedance assessment, or a lower body or an upper body, or you could have more than 2 electrodes and you could get a better assessment. But the individual is just going to be laying down pretty easy. All right, the electrical signal comes in, comes out, and there's an assessment. For me, this is the easiest way to do it. I don't have to lift a shirt up. I don't have to pinch anybody. I don't have to have them underwater. They don't have to have any clothing. This person's just laying down, and now they've gotten this bioelectrical impedance so effective that I don't even need to have this lab bench or whatever. I just do it on my scale. And this is how those bioelectrical impedance scales work. Person just gets on the scale. The electrical current comes from the scale. Like, so my scale looks something like this, like that, where I have my, it tells you what your body weight is here. And then it has just like a little metal piece and a little metal piece. And they put their feet right around the little metal piece here, put their foot here, and then they put the other foot here. It's got to be on the metal piece. And then as they're standing, the electricity goes out of the scale, up the leg, down the leg into the other electrode. And then here it will tell me what your body weight is. It'll tell me your weight. It'll tell me your body mass index, right? It'll tell me your percent body water, so your water percent. It'll tell me your bone mineral density. It'll tell me your body composition. So I think that these assessments here, I usually keep track of every Wednesday, and I can use these as indicators of nutrition, all sorts of things. I can see whether or not their weight is improving. Now, they're young kids. They're young kids. All of their weights should be increasing to some extent. Right? They're young. Everybody should be increasing just because they're growing. Now, if I notice that a kid is not growing or not putting on weight, immediately I think that's probably some type of nutrition thing. All kids are growing. All kids should put on weight. If I have a kid who's maintained the same weight for 5 months in a row, there's something interesting there to me. Okay, I don't really use body mass index too much at all, because body mass index values are based on calculations of the normal individual. And remember, it's body weight divided by height squared. And this body weight, height squared, this body weight is in kilograms. but I can't tell whether or not that's kilograms of fat-free mass or fat mass or some type of combination thereof. And for my athletes are definitely not at the typical body composition. My athletes are like 5% body fat. So I think that using body mass index as an indicator of anything for my athletes is probably going to be misleading because they have such atypical body types that this is probably not really realistic. It will tell me their percent water and how much water they drink or whether or not they're dehydrated. That's helpful, especially during summer, especially if they're outside on, a football or soccer field with, and they're sweating a lot. I can figure out whether or not they need to drink more water. I also can see their bone mineral density. Now, I don't really use any of the values that I get from my kids on these scales at all as absolute values except for their weight, because I don't think that this scale is designed for gymnasts. I think that these scales and the mathematics in these scales and the computer chip in the scales is geared towards the normal adult, right? The 5'8", the body composition 20. They're not, the mathematics in this scale are not geared towards a hyper physical athlete who's in the gym for 4 hours every day at 10 years old. So for me to use these values that I get on this scale as absolute values of body mass index or percent body weight for my athletes, I think is not really fair. But for the average shaped normal individual who's doing reasonable activity or whatever, this bioelectrical impedance scale gives me all of these variables. So that's why I use it. Get the scale, it's $29.99, and then you never really have to think about the body composition of hydrostatic weighing. I just bring it with me. I put it in my backpack, and if I have a client, I'm just going to do these things. Every Wednesday, I bring this to the gym. Today is Tuesday, but tomorrow I'll bring my scale in. I usually keep it in the gym, and we do this. So that's the easiest way for me to suggest that you guys get body composition. And I think with that, I think that's probably where we need to go in terms of our assessments with body composition. Okay, and when you are measuring body composition, what we're going to be looking at, again, is your percentage of fat-free mass. Fat-free mass is going to include everything from bone to tendon, ligament, muscle, cartilage. All right, and remember, fat-free mass is important because it's the fat-free mass that is going to be metabolic, is going to be utilizing or is used for, or is going to be using the nutrients, right? Your fat stores don't burn energy. It's your fat-free mass, particularly your muscle, that is going to be involved in burning down your carbohydrate, proteins, and fats. So your muscle is what they call an active material. It's active. It's doing something. It's not dead weight. Fat is dead weight. It doesn't do anything. It does allow us to store a lot of energy, but muscle is actually doing something in regards to burning down or metabolizing carbohydrate, protein, whoops, make that into a T, protein and fat. All right, so muscle mass is fat-free mass, and the fat mass is going to be your dead weight, your fat weight. All right, and usually with sport performance, we want to reduce fat because statistically, individuals who are endurance runners who have less fat perform better, but also many other athletes with less fat statistically perform better. But there are exceptions. Some sports need that fat because that fat is going to provide mass, and mass is going to provide momentum. So for some sports like football, sumo wrestling, having a high relative body fat might be better because they are more massive and it's more difficult to stop them. Right? Same thing with a weightlifter. A weightlifter might be able to use that mass to move and drive the weight towards the ceiling. Or a swimmer who has a higher percent body fat. Remember, fat floats. So it might be easier for a swimmer who has a higher body fat percentage to swim. So it's not always the case that we're trying to eliminate percent body fat. In fact, that's not the goal at all. In fact, if you're trying to get somebody to manage weight, we have two things that we're trying to do. We're trying to increase muscle mass, because if I increase my fat-free mass, then I increase my resting metabolic rate. And if I increase my resting metabolic rate, I can better manage. That should not be an R. That should be, if I can increase my fat-free mass, I can better manage my resting metabolic rate, but I'll also have more muscle to perform the activity and to make more forceful contractions. So I want my fat-free mass to go up. And I, in some instances, want my fat-free mass, my fat mass to go down. But that's not entirely the case. I do not want to eliminate the fat in my body, because the fat in my body is important for a number of different things. Okay, I believe it goes over this on the next slide. Let's see. All right, so your fat is important for a number of things. First of all, fat is essential for the absorption of fat-soluble vitamins. Fat is also important in thermoregulation. It's a very good insulator, and it holds heat in the body. Fat is also what your cytoplasm and your cell walls, your cells would have less structural integrity if it didn't have those lipid bilayers that made their cell walls. All right, so fat is important. We don't want to get rid of fat. We want to manage it. We want to reduce fat in our liver and in our organs, but we don't want to get rid of it. So if we're trying to manage weight, what might actually happen is as the individual increases the amount of fat-free mass and their fat mass reduces, remember, muscle weighs more than fat. So it could be the case that as an individual is trying to manage weight, that their actual body weight increases because you're replacing fat with fat-free mass. So losing weight is not necessarily the goal anymore. It's really managing weight. Understand how to reduce fat around organs and adipose fat so that you're not carrying around too much mass, but at the same time, increasing the amount of muscle so that I can perform the sport that I'm trying to perform more effectively. So it could be the case that losing weight is actually not what we're trying to do in the first place. All right, and it's not always the case that what we want to do is get rid of body fat. All right, so you'll notice that there is a huge focus on body weight, all right, weight standards, as opposed to healthy weight standards. Sometimes these weight standards are way too stringent and they're abused, all right? It is not always the case that weight loss is always good. And it's not the case that if I lose a little bit of weight, that more weight loss is going to be better. In fact, if I starve myself, I'm going to lose weight, but I'm going to also make it so that my tissues don't have nutrients they need to either synthesize actin and myosin, or if I don't have much caloric intake at all, I'm only going to be using my muscle mass as fuel. And if that's the case, I have less muscle. And if I have less muscle, I'm not going to have the strength in order to perform. And the unfortunate, or I guess extreme end of cutting weight with caloric restriction is that you can potentially lead to eating disorders and psychological stresses associated with eating. But it is the case that individuals competing who are at the bottom of their weight class oftentimes will result in injuries or reduction in immune function and health. So this graph right here shows that there's a bunch of different types of athletes. These are all elite athletes. And this graph shows that these two individuals were very good performers, the best performers. They were at 6% body fat. So the low end of percent body fat that we want to maybe take a look at is between, like, 5% is the lowest at all that we want to suggest, or even that we want to allow, not suggest. But this individual with 37% body fat here actually raced against these two individuals, and this person was able to win. So it's not the case that no body fat, that like reduction in body fat completely is 100% associated with success. All right, shows here that individuals who are doing the shot put, they need to have a little bit more mass so that they can push that mass into the shot put. So you'll notice that those individuals have a little bit of a higher percent body fat. Individuals who are doing distance running are typically a little bit lower, but that's not to say that they have to be 6%. This distance runner was quite effective at 37%. So somewhere between 5 and 30, 35% is our expected body compositions. But then again, an individual who is doing sumo wrestling is probably going to be much higher than 37%. But that's not to say that they're unhealthy. So the symptoms of severe weight loss are very similar to the symptoms of excessive training, overtraining, where you have your reduction in desire, motivation, difficult sleeping, anxiety, all sorts of these chronic fatigue type syndromes. All right, so oftentimes when I hear kids, they're afraid, they don't want to do this anymore, they're tired, they want to quit, they're lethargic, I can't do this, their face looks like it's sunken in, or they have chapped lips, or it's either overtraining or malnutrition. And all right, so let's keep moving on. And there's a number of other symptoms associated with weight loss, like psychological eating disorders, menstruation dysfunction, amenorrhea, bone loss, so that your bone becomes less stiff and becomes more brittle and has a much easier chance of fracturing when falls occur. And also a combination of issues associated with eating disorders, menstruation disorders, and bone mineral disorders can also present themselves. And for females, it's going to be even more impactful because males don't have to worry about menstruation issues. All right. This is one of the reasons why I do take my bone mineral density. Right, I'm not going to get absolute values, but if I do see that the bone density is decreasing or something, I can start taking a look at the nutrition, or just start asking questions to my athletes about their nutrition. So let's go into here. Let's go move away from body composition, and let's talk for the rest of the time about our nutrients and carbohydrate, fat, and protein. We'll probably talk about this it's right now 9:30. We'll probably go till about 10:15 talking about this stuff, all right? So we finished our discussion on assessing body composition, how we would do it. For us in this class, for you as remote assessors or people that might be doing this in field settings, it's my strong suggestion to go get yourself one of those bioelectrical impedance scales from Target. I saw one the other day, $29.99. It's been one of the best things I ever bought. So if I had to teach a lab on body composition, that's what I would do. Get on the scale and let's do it that way. Now, once we do have our assessment of body composition, it's indelibly linked to nutrition. So first we want to assess the body composition so that we can make it so that body composition values are efficient and effective for each sport. And each sport is going to be different, and each position within each sport is going to be different. For instance, a down lineman or an offensive lineman in football might have to have a higher percentage of body fat than the running back or the wide receiver, who probably wants to be as little weight as possible, so that they don't have as much force on their vertebrae as they run, or they can run faster. For me, my gymnasts, they need to be strong. They need to have enough muscle to be able to lift their body weight. But it's like the flip side of the coin. The more muscle they have and the more they weigh, the harder it's going to be for them to do a handstand or a cross, or the more impact on their vertebrae and their knees and bones they have as they run and pound on the vaulting board. So I want them to put on muscle mass so that they can be functional, but I don't want them to put too much weight on, because then they're too heavy to carry themselves around. Or if my athletes are only getting, 2,000 calories a day and they don't have enough calories to put muscle mass on, then I need to, like Cassie said last week, I need to change, or on Monday, I need to change my workout plan so that I can accommodate the number of calories that my athletes are getting. So the suggestion in terms of your nutrients is that you have about 55 to 60% of your calories come from carbohydrate. Remember, carbohydrate is gasoline, all right? It's wood to a bonfire. If I have wood, I can keep the fire going. If I want the fire to go hotter, I put more wood on. All right, but if, like my friend Josh, he has no idea how to put only a bit of wood on the fire. He has fun by putting all of the wood on the fire all at the same time. And you can do that, and the fire is going to burn very, very hot. It's going to burn very, very hot right now, but it's going to burn all of the energy in a very short amount of time. And in 3 hours, when I need the heat, I've burned all the wood, so I just can't produce the heat any longer. All right, so carbohydrate is like wood. Most of the time, I want my normal individuals to be about 50% carbohydrate, 30% fat, and 20% protein. But again, we're talking about nutrients for sport, and that will be a little bit different than the nutrients that we suggest for the normal individual. So for the normal individual, we should be about 50% carbohydrate. And you'll notice here that the suggestion is about 55%. So why is that the case? Well, because individuals who are doing sport are exercising more and need a little bit more gasoline. So you're going to plug this up to 55 to 60%. Now, you could also go as high as 70%. Some of the research in your book suggests as high as 70% can be effective, especially for very long distance runners. But that's to the extreme. For the most part, we want to be about 55 to 60% of daily calories, and I'll show you what that means. Your body does not store excess protein. So you don't need, if you're trying to put on muscle, to have 35, 40% of your diet from protein. You don't store excess protein, you urinate it out so you don't need excess protein. And for those individuals who are doing long bouts of long, intense endurance training, we might want to increase the fat percentages and reduce protein even more. So the carbohydrate and protein recommendations are based on your kilograms of body weight. So they're going to suggest a particular grams or amount of your carbohydrate, protein, and fat based on how much you weigh. So it's all relative to body weight. So I don't know if you can see right down here, but I did a little bit of mathematics, right? I'm 163 pounds. If I divide that by 2.2, I get 74 kilograms. So I'm 74 kilograms. I would assume that like maybe Drew, who weighs maybe, I don't know, 5-10 pounds more than me, is about similar to this. So these are the numbers that if Drew is in the middle of hockey season, all right, he would want to have this percentage of protein and carbohydrate. So protein, you'll see, is 1.2 to 1.7 grams of protein per kilogram. So for me, my fat-free mass, first of all, let's just take a look at my percent body fat. I'm 25% body fat. So of these 74 kilograms, 25% is fat, and 75% is not fat. So of the 74 kilograms, 18.4 kilograms, I'll just say 18.5 is fat. 18.5 kilograms of fat. All right, and at 25% body fat, the rest is going to be my fat-free mass, which is 55. 55.5 is my fat-free mass. And of that fat-free mass, 17% of that is bone. Everybody's about 17% bone. So 9.4 kilograms of bone. So just to give you a little bit of context, okay, I'm 18.5% body fat, 55.5 kilograms of fat-free mass, and 9.4 kilograms of bone. And remember, my resting metabolic rate, therefore, is equal to 500 plus 22, and this is in parentheses, so you do the parentheses first, 22 times your fat-free mass, which for me was my fat-free mass here, which is 55.5 kilograms. 55.5. And when I do this math here, let me just do it real quick. 22 times 55.5 plus 500. 22 times 55.5 is 1,221 plus 500 equals, my resting metabolic rate is about 1,721 calories. So I'm spending 1,721 calories just being alive, all right? So now at least we have a little bit of context of what this all means. So if I want to get the correct amount of protein in my body, I need to have 1.2 to 1.7 grams of protein per kilogram of body mass. And I'm 74 kilograms. So 74 times 1.2, okay? 74 times 1.2 is equal to 90. So that's 90 grams. And 74 times 1.7 is 125 grams. So 125 grams, so 90 to 125 grams of protein. And remember, grams of protein is equal to, each gram is worth 4 calories, right? So each gram is worth 4 calories. 9 times 4 is 360. And 125 grams is equal to 500 calories. So I want to have about 500 calories a day from protein if I'm performing sport. Now, carbohydrate is a little bit different. It's going to be anywhere from 55.5, 55.5 times 3, 55.5 times 3 equals 166. So this is protein. And carbohydrate is, so it's this value here, 3 times my 55.5. So that comes out to 166 to, and then it's going to be grams of carbohydrate. It's 12 times 74 times, 74 times 1.2, yes, 74 times 3 equals 222. I made a mistake. It's not the 55.5, it's my grams. So kilograms here is 74. So 74 times 3 is 222, not 166. All right, so I'm at 222 calories. So grams rather, 222 grams, and then it's 12 times 74 is equal to 888. So I should be anywhere from 222 grams to 888 grams of carbohydrate. But what does that mean? What is grams of carbohydrate? Remember, each gram has 4 calories. So 222 times 4 equals, that's 888 calories. So we'll just say 800 calories or 900 calories. 800 and then 888 times 4 is equal to 3,500 calories. So somebody who is doing physical activity should be eating about 360 calories of protein and 800 calories of carbohydrate. And this is if you're trying to do sport performance. Now, for an individual with a training goal of hypertrophy, I might want to have that on the high end. So during Drew's off-season hypertrophy training, where he's trying to make muscle, he's probably going to want to be on this high end of carbohydrates, 3,000 calories of carbohydrate, all right, but only 500 calories of protein. Okay, so the nutrients that you're going to be eating are carbohydrate, fat, protein, and then don't forget your vitamins and minerals, because it's your minerals like calcium, sodium, potassium, all of these minerals that allow for these chemical interactions and electrical signals to be conducted through ion and potassium ion channels throughout the body. So we need to make sure that we have not only carbohydrate, fat, and protein, but we have enough vitamins and minerals. So let's take a look at carbohydrates. Carbohydrates can be very simple molecules, which is only one molecule of sugar. Saccharide is sugar. Or you could have a molecule that has 2 molecules of sugar attached to each other. Or you could have molecules that are very, very complex. So monosaccharides, the easiest simple types of sugar are glucose, fructose, and galactose. But then you have disaccharides, which is like table sugar. Table sugar is a combination of glucose and fructose. You could have a poly. Poly is very complicated, or poly is multiple or many sugars attached to each other. And another word for a polysaccharide is a starch. And then you can even have more complicated polysaccharides that are known as fibers. These things break down very, very quickly in the body. And these, because they're complex chemical structure, these get broken down over a longer period of time in the body. The simplest monosaccharide, C6H12O6, is glucose, and that's what your brain and your muscles use for energy. The main utilization in your body of carbohydrate is as an energy source, as a fuel, specifically for your brain. Your brain only uses carbohydrate. So if you have a no carb diet and you're exhausted, tired, it's not because you need a nap. It's because you probably need a little bit more sugars for your brain to function. And remember that these carbohydrates are also, if they're ingested in excess without enough exercise, then your body wants to store these carbohydrates because they're valuable sources of fuel. They're not, however, very valuable sources of nutrients in many instances. Okay, and remember, any excess fuel is not going to be dumped. It's going to be stored. Like if I had excess gasoline, I would put it in a gasoline tanker, or I would keep it in my garage and use it for later. So your body doesn't want to get rid of carbohydrate. It wants to keep your carbohydrate. But if I am exercising and exercising to the extreme, eventually these muscle and liver glycogen stores will become slowly depleted. So in order for me to maintain the amount of carbohydrate I need in my body to conduct my daily activities or my exercise or sport performances, I'd need to have dietary intake of carbohydrate because I just don't have enough stored in my liver and my muscle to be effective. So I need to eat carbohydrate. All right, and depending upon the type of exercise, this carbohydrate that's absorbed might take longer or less time to replace the glycogen that has been utilized. So if I do a bout of exercise, I'm going to reduce the amount of muscle and liver glycogen, and that glycogen is going to have to be replaced. So I eat food, and within 72 hours, potentially, that glycogen can be replaced. Certain types of exercise, like eccentric muscle contractions, which cause this micro damage to the muscle, also have an impact in this reuptake or the replacement of carbohydrate, such that if my muscles are damaged because of eccentric muscle contractions, the synthesis or the replacement of that muscle glycogen is also reduced. So if I'm 163 pounds and I weigh 74 kilograms, so this is 74 kilograms, and this is, say, for instance, my athlete. My athlete is, he's 17 years old. His name's Yusuf. All right, and he's 74 kilograms. Multiply that by 10. It says requires 3 to 12 grams of carbohydrate per kilogram body weight per day. This is to maintain muscle glycogen. And he's working out like a dog. It's national championships in a month. He's trying to get into Arizona State University. So we're doing routines. We're doing a lot. So let's use 10. All right. That means that he's 74 kilograms, 74, all right, multiplied by 3 grams per kilogram. So I'm going to multiply by 10 grams per kilogram. So Yusuf needs about 740 grams of carbohydrate per day to be able to put muscle mass on. Now, 740, right, grams of carbohydrate per day is a lot. So 740 grams, let's multiply that by 4. 740 times 4 is equal to 2,900, let's just say 2,900 calories. So in order for him to be able to put muscle mass on and replace the glycogen each day that he's burning from workout, especially if we're in June and he's trying to put muscle mass on, he's going to need to eat about 2,900 calories a day. All right, so that means that at the very low end, 1 second, he's, I'm 10, 185 grams. 74 times 3, 74 times 3 equals 222. What does this 85 grams mean? 185 grams. 1 second, everybody. 740 divided by 4 equals, oh, that's what it is. All right. 74 grams. multiply grams by, all right. So I need him to get to 740 grams per day. All right, and just so you know, in one of these bags of rice here, there's 33 grams in a serving, but if I go like this, there's 3 servings per container. So it says about 3 servings per container, right? So it says 33 grams of carbohydrate, and there's 3 servings per container. So my math says that there's about 100 grams in one bag of rice. And remember, 100 grams, 1 gram of carbohydrate is 4 calories. So if there's 100 grams, then there's 400 calories in one bag of rice. So here we have, let's see, let's go back to here. Here's our math. We have to get to about 100. So I need him to get to 740 grams of carbohydrate. That's 10 grams per kilogram body weight. 740 grams, 2,900 calories. So every day I need Yusuf to be eating about 7 bags of rice. 7 of those bags of rice. I mean, he's not even going to want to eat 7 bags of rice. Oftentimes, he'll be like, dude, I'm not even hungry. I can't eat that much. And I say, I understand. But for an athlete, we want to make sure that they're eating not because they're hungry, not because the food tastes good, but because they have workout tomorrow. Oftentimes, getting to this 2,900 calories is going to be difficult. This is going to be a workout in itself to get to the amount of carbohydrate that an individual needs to put muscle mass on. So I'm going to need Yusuf to be pounding this rice. Okay? You might have heard your grandmother said a long time ago, don't let the gas tank go empty before filling it up. And your body is very similar. All right? If I have a relatively low carbohydrate diet, that's the red. All right? And I just take this and I connect this line to this line here. You can see that there's a reduction here. But if I take the blue line, not much of an appreciable reduction here. So these are individuals, they do the same thing. They put them on a 40-calorie diet first and then a 70% calorie diet. And you'll notice if I have a low carb diet and I'm doing 2-hour training bouts a day, which is more than reasonable, the low carbohydrate diet is not enough to keep my muscle glycogen levels consistent. Eventually, that low carb 40% diet is going to result in a depletion of the muscle glycogen. And eventually, I'm just not going to be able to have enough energy to do that bout of activity. And if I don't have enough energy from muscle glycogen, I'm going to get the energy from protein or my own muscle mass, and I don't want that. Now, I said earlier that the extreme is a very high carbohydrate diet, and you'll see this is 70% carbohydrate. But a higher carbohydrate diet is better in regards to maintaining muscle glycogen and giving me energy for a later bout of activity. So if you are doing high endurance training, 2 hours of moderate to intense exercise training, you could go up to about 70% of the diet for carbohydrate. So I don't believe a keto diet or a low carb diet works for people who are doing sports and trying to put on muscle mass. That's not the suggestion that I would make. For individuals that are not doing any daily physical activity and they're afraid of becoming obese because of stored excess carbohydrate, okay, maybe I could understand that. But our course right now is not on body composition for the normal individual. It's body composition and nutrition for sport. All right, so we want to make sure that we take a look at sport. All right. All right, let's move on. Some carbohydrates are going to cause a huge spike in insulin, and some carbohydrates are going to last for a longer period of time. So for instance, let's say this is thyme. This is thyme. There are some carbohydrates that are burned or that are broken down by my stomach so fast that what they do is they cause a very high spike in the sugars in your blood, glycemic index. Now, just for, I guess, clarification purposes, the simplest of all sugars is glucose. So what they do is they base all of these glycemic indexes based on how long it takes to burn glucose, or how much insulin, or the response of insulin in your body compared to glucose. So the response of your body to the amount of insulin it needs to process one amount of glucose is known as a glycemic index. Now, glucose, because it's our gold standard, is given a glycemic index of 100. And everything is pretty much compared to that. For instance, glycemic index foods that are high make your insulin response very similar, or act very similar to if you were eating glucose. For instance, if I drink a Gatorade has water and glucose in it. It's pretty much just drinking glucose. So let's say I eat 100 calories, or drink 100 calories of that Gatorade. Over time, what's going to happen is I haven't ingested any Gatorade. Right here, I'm going to make a different color, and that means when I ingest the Gatorade, boom, the Gatorade has been drunk. And right now, this is going to be my glycemic index, GI, all right, glycemic index. Right now, my glycemic index is normal. I don't have anything in my belly, and I drink a whole entire Gatorade. I drink 100 grams of that carbohydrate. There's nothing to stop the carbohydrate once it gets into my stomach and into my intestines. I'm going to have a huge spike in calories in my bloodstream, and the insulin is going to respond very quickly. There's going to be a huge dump of 100 calories in my bloodstream all at the same time, and my liver and my insulin response is going to be gigantic, and it's going to try to take all of that sugar and either use it or store it and get my body back to a normal glycemic index, or a normal amount of sugar in my blood. I could though have a banana, and a banana could have the same 100 calories, but the banana takes a lot longer to break down. So I'm going to have the 100 calories. I'm going to eat the banana. It's going to start to get into my bloodstream. There's going to be sugar in my bloodstream, but because the banana takes a lot longer time to break down than the spoonful of sugar or glucose, I'm going to have the 100 calories in my bloodstream for a lot longer time. The insulin is going to have to fight. I'm going to use some of the banana for fuel. I'm going to store a little bit, but the overall glycemic index is not as high. The spike of sugar into my bloodstream at one time was not as high. It's still the 100 calories, but the 100 calories are spread out over a longer period of time. Now, apples, pears, spaghetti, legumes, they take even longer to process. So you're going to get the 100 calories, but this time it's going to be 100 calories over a longer period of time. All right. And the low glycemic index foods make it so that some of the food is actually just still in my intestines and in my stomach breaking down, and it just doesn't get into my bloodstream as fast. So the insulin response is different. The storage of carbohydrate is different. The amount of energy that I have for a longer period of time is different. The sugar crash that I get with low glycemic index foods is different. All right, so you can layer your foods with different types of sugars. So I can have a meal that has low glycemic index foods like oatmeal. I can put in bananas and milk, and I can also put in a tablespoon of sugar, and I can have different layers of carbohydrates within one meal, and it can make it so that my pre-meal or my pre-exercise meal is a little bit more like engineered to last over a longer period of time. Okay, let's see where else we can go with this. So let's just take a look at carbohydrates and what carbohydrates, the amounts of carbohydrates, fat, protein. Well, let's go here. So in order to move forward with lecture today, I want to move a little bit forward to fat and proteins, and then we'll finish, okay? The most important thing about fat is that fat can be used as a fuel, and it's very important, all right? Fat, we do not want to eliminate fat. We just want to make sure that we're picking the right kinds of fat, all right? We do not want to have lots of saturated fats, okay? We want to make sure that we have fat because fat is a good fuel. It makes all of our cells and our nerve fibers, all right? And we need fat so that we can absorb some of the vitamins into our body. We just want to know how and what kinds of fats. We do not want to have fats that are high in cholesterol. Especially, we do not want to have fats that are high in low density lipoproteins. We talked about those earlier. You want to make sure that you're choosing the right kinds of fats. So you want to pick fats that are you want to pick fats that have low or zero trans fats, and we want to try to get away from unsaturated free fatty acids, okay? But again, fatty acids, free fatty acids are important fuels, so we don't want to get rid of them. We just want to make sure that we're not on fatty diets that are going to make it so that we have cholesterol problems and coronary artery disease. All right, and the last thing that I would do is I'll just show you a little bit about protein. All right, again, we don't want to have too much protein in our diet. We want to have more fuel. We want to have more carbohydrate, and we don't store protein anyway. So we want to have about 0.8 grams of protein per kilogram body weight. So what I did here is I'm just going to show you an example of different kinds of protein and how much protein I should be eating. Oh man, I hope I didn't screw this up from last night. Bummer, it did screw up. Okay, well, we'll figure it out. So in terms of protein requirements, there should be 1.2 to 1.7 grams of protein per kilogram body weight per day. So I am 74 kilograms, 74, and then 1.2 times 74 is 90. So 90 kilograms. And the 1.7 is 125 grams. 90 grams to 125 grams. So if Drew was in the middle of his hypertrophy phase and trying to put on mad muscle, he would have to be at about 125 grams of protein. Well, if I look over here, here's 125 grams of protein, all right? There's 6 grams of protein in an egg. There's 28 grams of protein in a chicken breast. There's 20 grams of protein in a can of tuna fish. All right, so if I had to say what you would need to eat to get to 90 grams, that's four cans of tuna fish. 4 cans of tuna fish. Now, That's not to say anybody wants to eat 4 cans of tuna fish. The point is, though, that's not a lot. That's not a lot of protein, 4 cans of tuna. That's not a lot. All right, it would be between, now each chicken breast is 28 grams. So we'll say 30 grams for a chicken breast. It's 3 chicken breasts to get to 90. At most, it would be 4 chicken breasts. All right, because each chicken breast is 30 grams of protein. So if Drew is at the very height of his strength and conditioning, putting on muscle mass, 125 divided by 3, that's only 4 chicken breasts. It's not very much. And in fact, in our Western diet, we get way more protein than we really need. I meant to actually show you, there's one other graph that I meant to show you back here. Let me see if I can find it. So we really don't need massive amounts of protein, and eating 30 eggs a day is not going to get it. It's not going to do what you need to do. All right. Here, let me just fast forward to here, because I did have, 1 second, metabolic. I did a bunch of research last night on, oh, here we go. On the kinds of food that you want. So we really don't need to have too much protein. 4 cans of tuna, 3 chicken breasts a day is enough at the very high end of what you're doing. Okay. Now, the chapter will talk about carbohydrate loading, and we're going to have to go through that, so I have enough time to get through the review for the exam. I think you guys can do that. The last thing today I want to do is take a look at this pre-competition meal. If you're trying to have an effective amount of energy before you exercise, you should have 200 to 500 calories 2 hours before competition. And a lot of that should be cereal, milk, juice, and toast. Well, kilocalories, 200 kilocalories, 500 kilocalories. So let's just take a look at this. 500, that's the most. If somebody's spending 5,000 calories a day, they're going to be spending, in that pre-competition meal, you want to have enough kilocalories to be able to spend during that bout of activity. So let's just say 500 divided by 4. 500 calories divided by 4, because there's 4 calories per gram. So I'm switching this 500 calories to grams. And then I want to see what grams of carbohydrate look like. So 500 divided by 4 is equal to 125 grams of carbohydrate. So before Drew plays hockey, all right, about 2 hours before his game, he should be ingesting 125 grams of carbohydrate. What does that look like? Well, for you, oatmeal, 1 cup is 32 grams. There's 32 grams of carbohydrate. There's 32 grams is equal to 1 cup of oatmeal. And he needs to get to 125 grams. So in order to get to 125 grams of carbohydrate before he works out, he could do smoothies, or he could do these things: 3 cups of white rice, 3 cups of spaghetti, 9 slices of whole wheat bread. Now, 9 slices of whole wheat bread gets a lot. That's why you have rice instead. Well, 4 cups of oatmeal, 5 cups of cereal, 5 medium apples and bananas, 4 cups of grapes, 4 cups of orange juice, 3 baked potatoes, 11 cups of cooked broccoli, or 10 tablespoons of sugar and syrup or honey. Now, obviously 10 tablespoons is way easier to eat than it is 9 whole slices of bread or 4 cups of oatmeal. Like 10 tablespoons, you could just mix in a glass of water, but that's pretty much what Gatorade is, right? So your pre-competition meal should be about 125 grams of should be about 125 kilocalories. Sorry, should be about 500 kilocalories divided by 4, 125 grams, and most of that should be carbohydrates. All right, so now the chapter talks about carbohydrate loading. Carbohydrate loading is good, but for individuals who are doing long distance training, for individuals who are doing like gymnastics or not huge long bouts of training, the suggestion is to eat these 500 kilocalories 2 hours before competition, and also make sure that you're replacing your muscle glycogen during activity with something like Gatorade or some other type of glucose replacement.